Hello and welcome back. We've talked about grading algorithms for so long. Today, let's take a quick dive into MSTs, that's the minimum spanning trees. And our goal for MSTs, I like to define our goal first so that we know exactly where our eyes should be. Our goal for the MSTs is to find a tree with the minimum age weight. So I'm just going to specify that because I like us to have the goal in sight from the onset. So our goal is to find the tree from a graph, of course, with the minimum age weight. Yeah, so that's our goal. So for our minimum spanning tree, first of all, we are going to be considering a graph that has vertices and edges. And before we continue, this video is starting with the assumption that we are quite familiar with what a graph is and what a tree is. But I'm just going to let's just take out about 2 minutes to kind of recap. The major difference between a graph and a tree is that a graph has cycles, a tree has no cycle. For example, this is, let's say, A, B, C, D are vertices. So we have this, right? This is a graph. The vertices are all connected. This is the edge. This is a vertex. So we have 4 vertices which are all connected using, in this case, we have about 6 edges. They are all connected. So this is a graph. But a tree, let's say this is a tree, would have this, we could have this, and this. This is a tree, right? All of the vertices are connected, but there is no cycle. So when we talk about cycle, we mean that we can take off from one vertex and come back to that same vertex. Let's say we have from B to D, from D to C, and from C back to B. That's a cycle. We have from A to B, from B to D, and from D back to A. That's a cycle. So a cycle, just think about it like starting from a vertex and getting back to that vertex without actually lifting your pen, right? Without having a break in the edges, connecting all of the vertices that get back to that original vertex, that get back to your starting point. So if we can go from A, C, D back to A without lifting our pen, right? That's a cycle. That's the intuition behind the cycle. You just go from one vertex to the other. This is a cycle. We left from A, go back to A without even lifting our pen. We went from this. We had this to be this. This is a cycle. But for a tree, trees have no cycle. So we have from A, B, C. We can't get back to A. Even though all the vertices are connected, we cannot get back to our starting point without repeating, without going through an edge which we have already gone through in an opposite direction. For example, if in a tree, if we want to get back to a starting point, let's say we go from A, B, and B to C. To get back to A, we'd have to go back in an opposite direction from C to B and then backwards. But for a cycle, we don't need to make this return movement. We We just move from one point to another. We just mosey on till we get back to the original starting point. But for a tree, which does not have a cycle, we cannot get back to the starting point except we go back through the edge from which we left the starting point. So, for example, let's say D. Once I leave D, I go from D to B to C, probably. I can't get back to D except I go backwards. So yeah, that's the intuition, the difference between your graph and a tree. That's not the only difference, but that's the main difference as it concerns this video. So for a minimum spanning tree, we'll be given a graph which has vertices and edges. Let's consider the graph below. We have, let's say, a graph with vertices A, B, C, D, and E, F. We have our edge, and the cost of this edge is 4. We have this edge which costs 1. We have this edge which costs 2. We have this edge which costs 4. We have this edge which costs 4, and we have this edge costs 3. Okay, and we have this other edge costs 6. We have this edge costs 5, and we have this edge costs 4. Right, this is a given graph, and we want to get a minimum spanning tree or minimum spanning trees from this graph. It's possible to have more than one minimum spanning tree from a given graph. So can you pause this video for 1 minute, look at this given graph, and then try to figure out what the minimum spanning tree would be? Okay, let's compare what you have to what we will have. So like I explained before I gave this graph example, the difference between a graph and a tree is that a graph has cycles and the tree has no cycle. So a tree is a graph that is connected and has no cycle. The tree is a graph that is connected and has no cycle. And a minimum spanning tree is a tree that contains all the vertices, but the sum of the edges of the weight of the edges of MST is the minimum. So for our MSTs, we'll be calling it MSTs from now on, minimum spanning trees. For our MSTs, we want, first of all, we want to tick some boxes. The first one, we want it to be a tree, right? And the second box we want to tick is that we want the edges of the tree to be minimum. Those are the two boxes we want to tick. We want it to be a tree, which means no cycles, number one, and all vertices are connected. All vertices are connected, but no cycles. All vertices are connected, no cycles. We want to tick this, and then we want all the edges to be minimum. So let's look at this one. Let's go from A to C, which is 1. We go from B to D, which is 4. We go from C to D, which is 2. I have F. So this goes here, I have 4. And this goes here, I have 5. This is a minimum spanning tree. The total weight of all the edges would be 1 plus 4 plus 2 plus 4 plus 5, which would be 16. Right. And if we look carefully, we can see another minimum spanning tree from this same graph. If we, instead of connecting B to D, we connect C to B, which has the same weight, we have another minimum spanning tree, which also has the sum of edges, 16. So let's confirm that this checks these two boxes. Number one, we want to check that this is a tree. That is, it has no cycles and all the edges are connected. So all the vertices, I meant to say, sorry, are connected. So we have A, C, B, D, E, F, all are connected. We would have had a disconnection if, for example, this was missing. If we ever have a vertex that has no edge touching it, then there is a disconnect. So if we had something like this, then this is not a tree. So all the vertices are connected. That checks off. And there are no cycles. Let's check. E, F, C, D. I can't get back to E without visiting the edges D, C, F, E. So because I can't go back to E without visiting the edges from E to D, I have no cycle. Let's confirm for the others. I have A, B, A, C, B. I can't get back to A. I have C, B. I can't get back to C. Through a new route. I have C, D. I can't get back to C through a new route. So yeah, this checks off the second part of the first criteria. Now we want to check that the edges of the tree is minimum. Here I have 16. And for the first example, we also had edges 16. Now you want to confirm, is there any other tree I can get from this graph whose weights, whose edge weights would be less than 16? After you check carefully and there is no other tree, then whatever tree you have here is your minimum spanning tree. Let's stop to appreciate minimum spanning tree for a second. For example, if you have lines to connect to a network, we use the concept of MSTs because we want to reduce our cost for connection. We also see MSTs being used in the connection of road transport, oil pipelines, even computer networks. So this was just a brief introduction to MSTs. If you did like this video, please subscribe. It's actually free to subscribe. And I'll see you on the next one. And on the next video, we'll start talking about strategies for MSTs. We'll talk about the 3 main strategies and how to write proofs for them. So we'll catch up on the next one.